All right, hey, welcome back. Today I want to dive into something really interesting, and it has to do with cryptography and AI. So, an interesting intersection. Now, what I want to do is show you guys why I think certain things are just, well, actually, no, what I'm going to do is I'm going to dive right into the actual results of my experiments and then do the summary at the end. Basically, what we're going to do is we're going to talk to ChatGPT. We're going to use the different models and we're going to see what the results are. Now, what I want to do is start with something really simple with a little bit of a twist to prove my point. And it's going to be something called a Caesar cipher. A Caesar cipher is where you take a piece of text and then for each letter of the alphabet, you just shift it along. So it's like, say you've got the alphabet, you shift it 5 times, and the letters start from 5 along. So say 5, 5, Z, X, W, Y, V, something I think starts with V, the alphabet starts with V. Maybe don't quote me on that. Essentially, what will happen is that all the letters will be jumbled up and we'll have like an encoded message. And we're going to ask ChatGPT to decode it. So the stages I'm going to run through in this experiment, they're going to start with, I'm going to ask to decode it, and I'm going to supply the information about the cipher, and then I'm actually going to supply the information about the exact details of how the message is encoded. Now, what I want to talk about is how I think these kind of puzzles can be used as a measure of the effectiveness of reasoning engines. If we talk about reasoning, we're talking about looking at something and breaking it up into certain parts, and then looking at it from a conceptual level to, I guess, decipher the puzzle. Because essentially, what a Caesar cipher requires an understanding of is an understanding of letters and words and how they fit together. So, and the meaning behind them. So the words might have certain meanings that make more sense than others. So let's dive right in. Let's have a look at what we can get by asking various AI models in ChatGPT about how to decipher things. Let's go. We have our Caesar cipher here, which we're going to create. This is some text, the plain text. This is some text I have encoded. Let's make this. So I want to start with something really simple. I'm going to take this. It's a Caesar cipher of 7 shifts. So from A to H, there's 7 shifts to the right, and you can change this. You can make multiple shifts. You can add it to the previous one. The previous minus 5 was V. I actually, so I got that right. Let's go back to 7, so A to H. We have our encoded text here, and we're going to ignore foreign characters, so we're going to ignore spaces. So as you can see, this is the text. This is some text I have encoded, and this is the ciphertext, which is the result of this encoding. We're going to jump into ChatGPT, and we're going to say, I have some encoded text. Decode this, please. Decode this, please. Okay. And we're not going to tell it anything. We're just going to say what it is. And this encoded text appears to be a Caesar cipher if we shift each letter back by 7 positions. So look, it got the 7 positions right. So that's interesting. How it did that? Maybe it checked to see if a word matched. So maybe there was some history of ciphertexts. So we're going to do a couple of things here. But what you can see here, this is secret text encoded, right? So secret text encoded. And this is not what I wrote. This is some text I have encoded. And not only that, but the actual text itself is incorrect. Now, what I want to see is if a better model, A1 preview, can do better. Let's try a new chat. I want to try a new chat so we don't really rely on the previous results in any way. And we'll do exactly the same thing. This is some text I have encoded. Please decode it. Please decode it. Now, one thing that happened in my previous tests is this took a long time. I only did once just to verify the results, but I don't know if this will take a long time, but let's see. So basically, I did this whole process, as you can see, uh, for a long time, adjusting the letters, and I did it for about 1 minute, just sitting here doing, I think, this. So we'll just wait. Okay, here we go. So this is what it's done, shifted each letter. So this is interesting. When I last did this test, the results were completely different. It just gave me a one-line result. Let's see what it does here. And it got it wrong, right? This is some text I have coded. It's very close. This is some text I have encoded. I think the difference before, and I'll show you what I did before. I did this is some text I have encoded. So look, it failed to decode it, but it got very close. So there's something there in terms of the way that it resolves the the outcome. Maybe there is some particular algorithm that runs encoded text, but even so, it still got it wrong. If if we can reason that this is encoded, right, we're going to do this again. So we're going to shift, we're going to maintain the case here, and we'll shift it my 15, right? So it got very close, which is better than the result yesterday. But what I did yesterday is I did this in my test. So I actually put in some plain text, but I changed the letters to be nonsensical words, right? So we know what it is. This is because we know the meaning of the word, right? So this is what I mean when I talk about being able to reason about the meaning of things. So we got this. This is some text I have encoded. Please decode it. Now, this is where I think it fell over. So I did four shift. No, this is the wrong one. Sorry. I did 15 shifts. We can close this window. I did 15 shifts, and we're going to try this again with the letters changed to be just sounding phonetically the same, so we can understand the meaning if we listen to it. So I think this is why it took so long last time. Let's see, maybe it gets it quickly again. I'll have a coffee in the meantime. Yeah, so I think this is where it fell over because it would shift, it would try to find the pattern that matches the English alphabet, but for meaning. So it looks for meaning in the, well, it doesn't look for meaning. It tries to find letters that match for something that is commonly, I guess, in its recorded network of I guess matches. So because it can't find matches, because you don't really get anybody writing is, but it is an an effective strategy of just slightly shifting things to try and confuse the reader. It's a person who can reason can easily figure out that the words in the encoded message are what they are. Is because it sounds the same. Yeah, so this was what knocked it over last time. So last time I tried it with those altered letters, as you can see. The Z was changed to a Z and the C was changed to a K. So they were changed to, I guess, phonetically correct letters. So look, while that's going on, I want to jump back into open a new chat in. I'd open a new tab. Nope. Okay, so here let's see what it got. Add 11 numeric. So I got the number wrong here. This is interesting. This is the text I have been coded. Yeah, so look, it still got it wrong. And it got the letters wrong. It seems to have, this is some text I have been encoded. After decoding, it doesn't even match this Kotlin. Interesting. So it actually looks like it drew up some code to try and decode it, but the actual doesn't, it didn't. Yeah, no. Okay, so let's see. It said add plus cipher shift of 11, which is incorrect. So cipher shift of 15. So this try this is incorrect. Try cipher. This is incorrect. Try a cipher. Okay, let's try that again, right? So what I'm going to do is I'm going to create a new chat. And we're going to say this text has been encoded using a Caesar cipher of shift 15. What does it decode to? So I'm telling it exactly what the rules are around this encoding. And first, let's see, this following text. So we're saying it reasons, but it doesn't really reason, does it? I feel like the whole ChatGPT 01 is using some fluff to give us the, I guess, the term of reasoning, like mapping and shifting, decrypting the message. I think these are just words that are relate to doing this thing that you're talking about. So I don't think, yeah, let's see. Okay, well, let's see. Maybe, hopefully it gets it right this time. Subtract shift value modulo. So it's doing a different process again. As you noticed, like the table results of the previous one are very different to the results of this one. Okay, so it actually, this is some text I have encoded. It actually got it right for the first time, so that's good. So if we tell it exactly what the encrypted text is, Caesar cipher shift 15, then it works. That's pretty good. So if we, I mean, look, things like the Caesar cipher, Enigma, like the Caesar cipher is really simple. Now, Visionaire cipher, if I say this is text encoded using a Visionaire cipher, let's see what it does. We have key, the key is crypty, and the key mode is repeat. Okay, so I won't go into too much detail. A Visionaire cipher is a more polyalphabetic cipher. It's just more complex than a Caesar cipher. Go to 33 characters. Let's see what let's try this again with a new one. So that's pretty good. Like it actually resolved the encoding for the Caesar cipher. Yesterday I tried for ChatGPT 4.0 with that text. Same thing. I told it the number of shifts, and it still didn't get it right. So A1 preview, I guess, gets better results. Let's try with O1 preview this, and we'll jump straight to into what we're going to tell it, what kind of kind of cipher it is. This is a Visionaire cipher. Visionaire cipher. Vigene. 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 Cipher. Encoded message. Whoops. Let's get the actually encoded text. Which is, we'll just do that. Please decode it. Now, there are ways that you can work through a message to find the actual key. It takes a lot of effort and time, and in some cases brute force. But I'm interested to see what the results here would be. So here we go. And the next one I'm going to do is I'm going to do the same thing, but I'm going to supply with the actual key. Because we have spaces in this, it makes it easier to determine the words. but I really don't think this is. Look, I don't have high expectations for this at all. Okay, so while that's happening, there are even more complex ciphers. But I do want to talk a little bit about language translations. I know language translations are a big thing when it comes to the idea of neural networks. And one interesting thing is that in World War II, uh, one of the most difficult, if the one of the most unbreakable codes was Nahavo. I don't want to get that wrong. There was a Native American language that was used by the U.S. to communicate um, in when they were at war with the Japanese in the Pacific, and the Japanese could never break the code. But interestingly enough, the Enigma machine, which was supposedly even more which was a complex, I guess, a mapping of letters, was broken. But they used, see, this is the thing that I want to talk about in the summary, which is using mechanical and computational processes to solve cryptography puzzles. So yeah, this is deciphering with Visionaire. So this is what happened, I guess, when I did with the Caesar cipher yesterday. It took a long time, and the results were less than I guess suitable. The results is a determination of being able to solve something. Yeah, I don't know if there's any point in continuing this. I think this could take a while. It's saying the same thing over and over again, taking a fresh approach. You know, I'm not sure why it's taking so long, to be honest. Decrypting the message, deciphering the clue. So yeah, it's just repeating the same things and determining the plain text. So look, we're just gonna cut it here for a bit, and when it finishes, we'll get back to it. Okay, here we go. It's got something. To decode the visionary cipher, you need to determine the key length. Um, without the additional information, the key or more context, it's challenging to accurately decrypt the message. The visionary cipher relies heavily on the key for encryption. And the process becomes speculative. Answer, I'm sorry, but without additional information. So spent all this time, it couldn't do it. It couldn't resolve it. Not sure where it got to a point where it realized it couldn't do it. What if the so it just tells you how you can do it, right? And it doesn't have the algorithms or understanding to actually go run through it. So let's say if the Visionaire cipher key is crypty. The key is crypty. And let's see what it says here. What did I write? I wrote they is crypty. Can I stop this? Ah, I stopped. Yeah, let's stop this one. The key is crypty. Okay. So I think it's looks like a Chinese characters. So interesting. It's got this part here, right? Plain text letters are revealed as some text I have encoded, which is part which is part of it. You can see it's. So look, given the key, uh, going through the process of decoding it, it seems to have been able to have, it has enough information to go through the process of actually decoding it. Now, without the key, it can't do anything. And I guess for a visionary cipher algorithm, if you have the key, it's just easy. That's you just run through a set of steps to decrypt it. I guess that's the same thing with what about if we do base 64 like this? If we do base 64 and I go like this and say this is just like another test I'm going to do separate. So if we go and write a new chat, so this is encoded text. Please decode it. Now, I wonder if what it's thinking. I wonder what it's going to say. It's base. Interesting that with the ciphertext, with the Caesar cipher, I picked it up straight away that it was Caesar cipher. But this with base 64 encoding. Okay, yep. I guess it figured out it was, and yeah, that's pretty good. So it was able to find a match using the different types of encoding. So you got block cipher, cipher. So I don't expect this to be ciphers, ROT 13, Visionaire cipher, Bacon cipher. All right, guys. So let's jump to the conclusion. All right. So these things, in terms of puzzles, like anything that uses inference, can take a set of ideas, whether it's taking mathematical formulas and applying them to a certain thing, but actually processing the data and solving for a result. I think is a good way to measure the ability of something to reason. In this case, the way that it works with the collection of letters, it was able to decode the base 64 also, like find the right algorithm, base 32. So what does this mean really? The fact that the Caesar cipher wasn't able to solve it until I gave it the number of shifts. Same as the Visionaire cipher wasn't able to solve it until I gave it the number of the actual key. So I think if you can build, and this is one thing I think the military and intelligence agencies will definitely be working on these kind of things. And based on history, we can be sure that they're a lot more advanced than we have access to, right? So where it's likely that this kind of stuff is being used to decode, encode, and develop. You know, intelligence agencies kept a lot of the secret stuff from even World War II secret for 20 years after the war. So it was only until the 70s, late 60s, 70s, that all the stuff that was discovered during World War II in the intelligence agencies that we kind of figured out. So what the hell is going on in intelligence agencies now? I mean, it's hard to say. My gut feeling is that these kind of neural networks are already much more advanced. We have here, to what extent, I don't know. Like, could we have an issue with RSA and elliptic curve encryption? Maybe that kind of stuff can be broken, but I think the weakest link isn't necessarily even in the actual encoding and decoding. A lot of it has to do with social engineering. And during World War II, the Navy Enigma machine couldn't be broken, right? So they couldn't crack the codes, so they socially engineered to be able to find the keys. In the same way that this is not able to decode something until we actually give it the keys. So what's next? Uh, if this, yeah, it's hard to say. Like telling the future is, you can't really tell the future. But my kind of prediction is that these will get these models that work on ChatGPT or one preview. They're great tools, uh, but I mean, for me personally, again, I'm going back to the fact that I'm using this just really for as a reference manual, help increase productivity without having to spend time trying to find information. But at the same time, I actually enjoy the process of reading about certain things that might give me insight. So if I want to know about Python, C++, or any particular language, I'll probably sit down with a few examples and just work through them and learn a bit more about the language. But if I need to rush something out, then if I need to remember how do I reverse a list quickly in Python, I might go and ask a large language model. But for consumers, and look, that's that. I think we've talked. There's been so much stuff about AI that people are probably sick of it. But I wanted to see if we could use cryptography as a reasonable measure for the ability of these models to reason. And I think they're very much lacking. Because I think the problem lies in the fact that it gives you the result with such a sense of confidence when it's wrong. So when it doesn't got the number of shifts wrong in the previous tests, and it got the actual message wrong, but almost correct without giving it the actual shift number. So on that note, I think that's it for this week. I'm going to continue on with cryptography. Maybe do another cryptography video next week. Who knows? But for now, thanks for listening, and I'll see you at the next one. Bye.